We'll now discuss the final phase of the compiler process, which is code optimization. Back in the early days, when Fortran and COBOL were just being introduced, it was very important not to waste any resources when running programs. And this is because there really weren't that many resources available, nowhere near as much as what's available today. There was a lot less memory, a lot less CPU power back then. I mean, we're talking about maybe a couple kilobytes at most, but there really wasn't a lot of room to work with. So we really couldn't have programs wasting any time or wasting any memory. And in fact, believe it or not, back then it was actually cheaper to have the programmer optimize the code instead of trying to have the compiler optimize it. And this is because it was cheaper for the programmer to decide which instructions ran faster and use those instructions in the assembly programs. The compiler would take a lot more time to try to figure out what instructions ran faster, but a programmer could take a look at it and go, this one runs faster, so let's use that in our assembly program. And this whole process of trying to improve the time and or the space efficiency of the translated code is what we call code optimization. For modern compilers, the exact opposite is true. It's actually now cheaper to have the compiler optimize the code instead of the programmer. And one of the reasons is because hardware costs are a lot smaller than they were 50 to 60 years ago. Another reason is because instructions run a lot faster. So if we were to reduce 1,000 lines of code today, that may only save 0.00001 seconds, a very small fraction of time. So it's not as vital to have a programmer trying to go through and see what lines of code can be cut. And another reason is programmer costs are rising. I mean, it's actually becoming more expensive to have programmers work on something than the machine itself. So it's actually a lot cheaper to have the compiler take care of it than trying to have a programmer go through all of the translated code and see where there's room for optimizations. The goal in compiler design today is to provide a wide array of compiler tools that simplify the programmer's task and increase his or her productivity. So this includes several different types of tools, such as the visual development environments that use graphics and video to let the programmer see what's happening. We have sophisticated online debuggers, and these would help programmers locate and correct errors. We have reusable code libraries. These will contain a large collection of pre-written program units. And then when the compiler is embedded within a collection of supporting software development, such as debuggers, editors, toolkits, and libraries, it's called an integrated development environment, or sometimes also known as an IDE. So it's these types of programmer optimizations rather than code optimizations that have taken center stage in language and compiler design. There are two types of optimizations. We have what's called local optimization, and this is relatively easy and it's included as part of most compilers. The second type is what's called global optimization, and this is a lot more difficult, and it's usually omitted from all but the most sophisticated and expensive production level optimizing compilers. In local optimization, the compiler looks at a very small block of instructions. Usually this is just like anywhere from 1 to 5 instructions. And what it does is it tries to determine how it can improve the efficiency of this local block code without any regard for what instructions come before or after the block of code. It's as if the compiler just placed a tiny window over this code, and it's only going to optimize the instructions that's inside this optimization window. Now, there are several different types of local optimizations that we're going to talk about. We have what's called constant evaluation, we have strength reduction, and then we have eliminating unnecessary instructions. With constant evaluation, the idea is that arithmetic expressions are fully evaluated at compile time whenever possible rather than execution time. So let me give you an example. Let's say we have the high-level statement x equals 1 plus 1. A non-optimized translation of this would be to load 1 and then add 1 to it and then take that result and store it in x. However, the compiler can recognize that we have two 1s here that we could evaluate at compile time instead of while the program is running. So instead, we could say something like load the value of 2, since that's 1 plus 1, and then store that into x. With strength reduction, we replace slow arithmetic operations with faster ones. So like, for example, on most computers, incrementing is faster than addition, and addition is faster than multiplication, and multiplication is faster than division. So whenever possible, the compiler replaces an operation with one that is equivalent but executes more quickly. Let's take the example of x equals x times 2. We just mentioned that addition is usually faster than multiplying. So we're going to replace x times 2 with x plus x. So the non-optimized translated code would be load x, multiply it by 2, and then store x. But it's actually faster if we just add x instead of multiplying by 2, and then take that result and store it in x. The third option is to eliminate unnecessary operations. So the idea here is that we have instructions that are correct, but they're not necessary. So we just discard them. So let me give you an example. Let's say we have the code x equals y and z equals x. So we're going to assign y to x, and then we're going to assign x to z. Now, the key thing here to recognize is that the way our memory works is when a value is stored in a register, we don't need to load that same value again. But if we read the lines one at a time, if we translate each statement individually, there may be some unnecessary load and store operations. So if we take a look at the non-optimized version of this, we would load y into a register and then store it into x. But then we would load x into the register. But that value is already there. That value is y. We don't need this load operation again. We can just simply cross that out. And the final result is we still store it in z. So what we do instead is we just take out the load x operation because we already have that value in the register. There's no need to reload it again. Let's try out our code for x equals y plus z and see if we can optimize it a little bit. So here's what we had before. So we had our 4 variables. We loaded y and added z to it. We stored that in temp. And then we loaded temp and then stored in x. So we can see right away there are a couple things we can do. So the first thing is we have unnecessary store and load operations because, well, I mean, if we store something in temp, we're eventually going to store it in x anyway. So we don't need to store anything in temp, and then we don't need to load it back into temp. So if we store something in temp, well, we don't need to load it back because that result is already in the register, so we can take that line out. And quite honestly, since the result's going to be stored in x, we're going to take whatever is currently in the register. Well, that value is already in the register after we add z, so this store operation or this store instruction is no longer needed. So we can take that out too. And then there's another optimization in that, well, we're not using temp anymore, so why do we need memory for it? So we can take out this line here as well. So this would be the final version of the code where we don't need the temp variable anymore. We just load y, add z to the register, and then just store that in x. So we only need x, y, and z. The second type of optimization is global optimization, and it is much more difficult. In global optimization, the compiler looks at large segments of the program, not just small pieces, to determine how to improve the performance. The compiler is going to examine large blocks of code, such as while loops, if statements, and procedures to determine how to speed up the execution. And this is a much harder problem, as I said. It's harder for both the compiler and for a human programmer, but it can produce a large amount of savings in time and space. Let's take a look at an example and see how we can use global optimization. So here's some code where we're trying to compute the sum 2x0 plus 2x1 plus 2x2 all the way to 2x 50,000. So this may be something that an inexperienced programmer might actually write because this loop actually includes the time-consuming multiplication operation 2 times xi inside the while loop. I mean, it'll work, but it's not efficient. If we move the multiplication operation outside of the loop, it's actually possible to eliminate 49,999 unnecessary and time-consuming operations. So a good optimizing compiler would analyze this loop and restructure it to something like this. So notice now that we multiply by 2 after we get the sum. So we're still computing the sum inside the body of the while loop, but then we just multiply by 2 after the loop. So this eliminates a lot of operations. So I mean, such restructuring requires the ability to look at more than just a few instructions at a time. The compiler just can't look at only a small optimization window in this case, but it must be able to examine and analyze large segments of code. So this requires a compiler that can see the big picture and not just a small scene. So seeing this big picture is difficult. That's why we're saying it's harder. And many compilers are unable to do the type of global optimizations that we just talked about. We'll finish the lecture by going over one extremely important fact about code optimization. It cannot make an inefficient algorithm efficient. Sorry, it's not going to happen. As we talked before about algorithms, the efficiency of an algorithm is an inherent characteristic of its structure. It's not something that is programmed in by a programmer. It's not something that is optimized by a compiler. It doesn't matter how much you optimize an inefficient algorithm, it's always going to be slower than a non-optimized efficient algorithm. For example, you can take a sequential search algorithm and have it written by a team of world-class programmers and have it optimized by the best compiler out there. It's still not going to run anywhere near as fast as a non-optimized binary search program written by first-year computer science students. So code optimization should not be seen as a way to create fast, efficient programs. The goal is actually achieved when we decide which algorithm to use. So think of optimization as more like the icing on a cake, where we take a good algorithm and we just make it a little bit better. I mean, that's the whole point of optimization. We're trying to make good algorithms just slightly better.